So to generalize our rules for how to use partial fractions to decompose, um, let's consider that we have a polynomial n of x in the numerator and d of x for denominator. And the first thing we consider is if the degree of the numerator is greater than the degree of the denominator, the first thing we want to do is actually just divide, so long or synthetic division, and then we only need to use partial fractions for the remainder. Okay, but if the degree on top is bigger than on bottom, you want to divide first. And I believe we have an example of that later. Yeah, okay, so we'll get to an example where we have to divide first. And then if that's not the case, then we want to factor the denominator to irreducible powers. Just real numbers. So in other words, if I had x squared plus 1, I would not factor that as x plus 1 times, or x plus I times x minus I. And then for every linear factor that we have written as px plus q raised to the mth, funny, we're going to use partial fractions on that like this. So let's say that I actually had px plus q, so p and q are constants here, and m is to the third power. So on the examples that we did before, all of the linear powers were raised to the first power. So this is x to the first, where's my cursor here? X to the first, x plus 3 to the first, x minus 1 to the first. But with these, if I have something raised to a higher power, then I'm going to write the partial fractions as, well, here, we'll just use a, because I'm not going to have 26 of them. So a over, there we go, a over px plus q plus b over px plus q squared plus c over px plus q to the third plus however many terms, or whatever this degree is, that's how many fractions I need for the linear parts. Okay, so in other words, and I do have an example that we'll do here in a minute, but so let's say that I had, let's say that we had some numerator over 2x minus 3 to the third. Okay, we would write that as a over 2x minus 3 plus b over 2x minus 3 squared plus c over 2x minus 3 cubed, because I would need up to this many, but I don't do 3 separate linear terms. I do the polynomial to the first, to the second, and to the third. Okay, and like I said, we have an example coming up where we have a linear factor raised to a higher power. Okay, then if we have a quadratic factor, we are going to use partial fractions, but we're going to have a linear factor in the numerator. Now this, well, here, let me show you. So for example, for example, when we split this, we'll have something like ax plus b over px squared plus qx plus r. Okay, and then if I had more than one quadratic, or if I had a quadratic factor that was raised to a higher power, then I would need to repeat this process that I did up above. So then I would have plus another linear expression, so cx plus d over the quantity px squared plus qx plus r squared plus ex plus f over px squared plus qx plus r cubed, etc. for however many factors, however many times the factor px squared plus qx plus r showed up. Okay, now you're not going to have problems to do where you have like a quadratic trinomial raised to the 5th power or anything like that, but that would be the process where you would continue to expand that. Okay, and then we still would use one of the methods that we used up above to solve for all of our coefficients. Okay, so let's do an example here with a linear and a quadratic factor in the denominator, and it is already factored for us. Okay, so we're going to write this, or we're going to decompose this as something over x plus 1 plus something over x minus 2 plus something over x minus 2 squared. Okay, and like before, I'm going to move over here to do the algebra. So we have 18x squared plus 5x minus 4. Okay, and that's going to be equal to a. I'm going to go ahead and multiply. My a is right here, so I'm going to multiply it by these, or by what's necessary for the common denominator. Actually, nope, strike that. I'm not going to do that yet. I'm not going to do two steps at once. So this is over x plus 1, x minus 2 squared. Okay, so, sorry. A over x plus 1 plus b over x minus 2 plus c over x minus 2 squared. Okay, so then multiplying, getting a common denominator everywhere, or actually multiplying by all three of these factors, okay, this whole denominator cancels out because we only care about numerators. So we end up with, let's give myself some room here, 18x squared plus 5x minus 4 is equal to, all right, so here x plus 1 cancels out, and I have x minus 2 times x minus 2 left over. So that's going to be, we're multiplying by x, I'm going to go ahead and distribute up here. So x squared minus 4x plus 4. So we'll have ax squared minus a times 4x plus 4a, and then the b term already has an x minus 2, so I'm going to be multiplying by x plus 1 and another x minus 2, which is going to be x squared minus x minus 2. So distributing the b, I get plus bx squared minus bx minus 2b. Okay, and then for the c term, both x minus 2 factors will cancel out, and I just have an x plus 1 left over to distribute, so I have cx plus c. Okay, and I'm using the same method I did on the first video, the first example, and so I'm going to write a system of equations using the coefficients. So looking at my quadratic terms, I've got an 18 here, an ax squared, and a bx squared, so I have 18 is equal to a plus b. And then for my linear terms, I have a 5 and a negative 4a and a negative b and a positive c. So 5 equals negative 4a minus b plus c. Okay, and then for my constant terms, I have a negative 4 equals, and I have a 4a minus 2b plus c. So 4a minus 2b plus c. Okay, so I have a system of 3 equations and 3 variables. It is going to take me a little bit extra algebra to solve this, but I can handle it. So I'm going to start by combining these 2 equations, okay, and let's see, I'm going to subtract them so that I can cancel out the c term, and so I'll have 5 minus negative 4 is 9, negative 4a minus 4a is negative 8a, negative b plus 2b is positive 1b, and then c minus c is 0. Okay, so now I'm looking at these 2 equations, and I'm going to subtract again. Let me rewrite this. So 18 equals a plus b. I'm going to distribute a negative 1 to this equation, so I get negative 9 equals positive 8a minus b. Okay, adding these together, that's gone. This is a 9, this is 9a, that's convenient. A is equal to 1, we like integers, okay? And then I can plug that back into my first equation, so that means 18 equals 1 plus b, so b is 17, and then plugging it into either the second or the third equation. I'm going to use the second equation. I have 5 equals negative 4 times 1 minus b, so minus 17, plus c, this is a negative 21, so adding 21, I get that c is equal to 26. Okay, so my coefficients, or my numerators then, are 1, 17, and 26.